Getting real up in here. They're talking about taking out loose ends. That means me and you. Karen, watch out. All right.
I know where Karen is almost every night. She's at okay.
Yeah, they're ratting you out. Applebee's.
Sorry, she's at Applebee's.
Clarify. There we go. 2021. Fine. It's okay. All right. Hey, today we're going to talk about homogeneous equilibrium. All right. Now, before we had 9 weeks projects and all that good stuff last week, we started talking about writing an equilibrium expression. All right. So, for example, if I gave you something like this, so here's your equation. So we're starting here, and if you wanted to title today's notes or something, you could just say it's homogeneous equilibrium. Homogeneous equilibrium. Hey, Kieran, I'm using my markers.
That's awesome.
Yay! Love them. Okay, so homogeneous equilibrium, you got N2O4. Oh, O4. Yeah, I can have it. That's a 4. Okay, so N2O4 gas. Okay. And what I'm going to do is I'm going to draw a double-sided arrow. If you see a double-sided arrow, that means it's in equilibrium. It can go in both the forward and the reverse reactions. And it's going to produce 2 NO2 gas. Okay. So a mole of this dinitrogen tetroxide would produce 2 moles of nitrogen dioxide, but it will stay in equilibrium. So as it goes forward, it's going to start to break down again. It's constantly going back and forth. Okay. All right. So today what we want to do is we want to figure out how to write an equilibrium expression and learn how to find the equilibrium constant Kc and Kp. Okay. So we want to know how to find Kc, which is going to be the equilibrium constant, for concentration, so Kc is the equilibrium constant for concentration, and we also want to learn today how to write Kp, okay? Kp is going to be the equilibrium constant for pressure. Okay. So let me ask you something though. Okay, if we're talking about Kp or equilibrium constant for pressure, when do you think this would apply? Like what state of matter would you be able to find a Kp for? Solids, liquids, or gases? Gases. So Kp is only going to apply when there are gases. So only for gases. We're only going to find Kp if there are gases present. Okay? All right. So if I ask you to write the equilibrium expression for this equation right here, we're going to review this. We only did like one of these problems right before 9 weeks projects started. So we're going to go ahead and write this equilibrium expression for this reaction together. And the way that we're going to do that is we're going to say Kc equals, and we're going to represent products over reactants. You're always going to do the product side over the reactants. So we're going to write it like this. Look at your products. You're going to write NO2, and we're going to write that in square brackets like this. And we're going to put it to the second power. So NO2, and we're going to write it to the second power divided by N2O4.
Why do we have to put them in square brackets?
Good question. The square brackets, whenever you see those like in chemical writing, like equation writing, a square bracket indicates concentration. So like molarity. So like whenever you see a value here in a minute, like when I start giving you numbers to put in here, you'll see it represented like 1.5 capital M. So that means you got 1.5 moles per liter. That tells you how concentrated it is. Okay. So that's how we're going to write that expression. So the square brackets represent concentration. The little exponents are just the coefficients. They turn into, the coefficients turn into exponents. Okay. So that's how we would write the equilibrium expression for Kc. All right. Now, one thing we're going to know here is that you can also do the same thing if you're trying to figure out Kp. But here we're just going to write, you would write the pressure, and we're going to square it of NO2. And of course, we're not going to put that in brackets, right? Because it doesn't represent concentration. We would just write pressure. It would be in a pressure unit like atmospheres or torr or something like that, okay? And then pressure of N2O4. So these are two ways you can write equilibrium expressions. This one's for concentration. This one is for pressure. Okay, the brackets represent moles per liter. This is just going to be in a pressure unit. Okay, but you write them the same way. Products over reactants, and then raise them to whatever power the coefficient is. Okay, so another thing that we need to make note of, or that we need to know, is that Kc, your equilibrium constant of concentration, does not necessarily equal Kp. They're not always going to be the same values. Okay, so Kc does not necessarily always equal Kp. Okay, but in cases where it doesn't, there is a relationship that you can use. Okay, so if they give you, for instance, the concentration, the Kc, and say, can you find the pressure constant based off of your concentration constant, your equilibrium constant, your Kc, you can if you have certain things, okay? So here's what you would do. Just know that Kp would equal Kc if you could multiply it by the gas law constant R times the temperature that it's at. So we're going to say Kc times RT. And then we're going to raise that power, or raise that to the power of delta N. Delta N. I hope you can see all that, Karen. All right. So I'm going to label some stuff here. Okay. R is going to be 0.0821, right? That's our gas law constant. Remember, like liters, ATMs, Kelvin, mole. T, of course, is temperature in what unit? Kelvin. Very good. That's going to be in Kelvin. All right. And then delta N, that's going to be our change in the coefficients. And what you're looking at, hey, there's she. Yay! She did get a cap and gown. Oh, did you already call your mom and tell her? What? You're supposed to. As soon as you get your cap and gown.
Oh, she knows that it was today.
You put the hat on this, send her a picture and see if she writes back like with tears. That's what you do.
No, she already cried yesterday, so
Oh.
can't do pictures today too.
Oh. Hey, if you don't have any homework to do, the lab, if you can just get all of the crap and like all of the chemicals, put them on that end of that table, and all the glassware to the wall, because I've got to do a lab in here tomorrow.
That's for the
Yeah, sorry. Yeah, it's true.
Do it.
Do it. Yeah, whip sound. I never have been good at that. Whoops. Oh, just get a whip.
Yeah,
Jimmy's feeling violent today.
Pull out, press a button, and
But just have it.
Just make the noise.
Yeah, but see, I would do it wrong.
It's like on the floor.
Yeah,
knock out a kid.
my mom used to have I'll tell a story of my mom here. We've got time, right? Mom,
Or just water.
I don't really know what that. Oh, is that some of you guys' stuff? Let's go with salt. You can put it down the drain and just run some water.
Unless there's something in there.
Yeah.
That's all.
Let's possibly it's acid. I don't know.
We'll
Uh,
know if there's something wrong.
Anywho, Mom used to have like this belt. Mom hardly ever would spank us with a belt. Like if we got a spanking,
Why are you
she'd
talking in third person?
spank us with a belt.
She was,
No,
it's
you said
just-
mom spank. Okay. wait.
My mother.
if she was like, if she was like,
Well, that's
Mom
the thing. I
spank
thought you were
this
talking about you because you
level,
looked.
Oh
there.
no, sorry.
What is happening?
No, I was trying to make sure she didn't get acid on her fingers. Not that it's acid. It's probably not. Anyways, so my mom would have a belt though, and so all she would have to do, like if me or my sister was causing trouble, she would take that belt and just, you know how you can put it together and whip it like that. Holy cannoli! Like still, I can hear that sound today, and I'm like, oh. So, yeah, maybe I need to get a whip or a belt.
stop.
Yeah. See, it's just not as.
Sorry.
You're gonna do that, and like the principal's gonna walk by, and she's gonna be
Yeah, she's fired.
like,
All right.
Oh, no, I'm not.
Yeah, I know. Watch this. All right. Hey, this Delta in ring. You what?
Could I just throw these in the trash?
Yeah, I think Nikki, y'all don't want those, right? Like souvenirs.
Oh, no,
Okay.
those are your back.
Yeah, just trash them. This is the change in the coefficients. Change in the coefficients. And you're going to do the products coefficients minus the reactants coefficients. Okay, so you're just going to take the product coefficients minus the reactant coefficients. That's going to be your delta in there. Okay. All right. Now, just to add a couple of things here, all right, a couple more things that we need to know, and then we're going to start some practice problems, some example problems together. A couple more things that you need to know. First of all, and I'm running out of room here, so I'm going to do this. First of all, just know that K has no units. K has no units. It's simply a value to try to tell you if the reaction would favor the products or if it would favor the reactants. Like when you find this expression, when you find this constant, is that going to tell you that the reaction is going to keep going forward and producing more product, or would it lie back to the left? Okay. And do you remember what we said before 9 weeks? If your K is greater than 1, so if K is greater than 1, we said a couple of weeks ago, then the product side is favored. So if K ends up being greater than 1, your product side is favored. So in other words, the reaction would keep on moving to the right, just like a normal reaction would. If K ends up being less than 1, a number less than 1, your reactant side would be favored. It would go in the reverse direction. Okay. All right. The only other thing we're going to add. Okay, so I'm going to box in. This is what we're going to focus on today in our practice problems. We're going to write equilibrium expressions for Kc. We're going to focus on using this one to write equilibrium expressions for Kp. And we're going to focus on this one as well, which is your how to find Kp if you've got Kc and temperature and stuff like that. Okay. So these are the three main formulas and the three expressions that we're really going to focus on today. But let's go back to this one for just a second. In the event that you ever have like your delta N of just being 0, like if you do the math and then you do the products minus the reactants with the coefficients and it just ends up zeroing out. In that case, if your delta N ever equals 0, then at that point, Kc really does equal Kp. Okay. if your change in N, your change in your coefficients does end up equaling 0, in that event, then of course Kc would equal Kp, okay? All right. So here's what we're gonna do. If you have a book and you want to open it up and follow along, I'm just doing practice problems straight out of the book. If you don't have a book, or if you don't want to get up and get one, I'm just gonna write up the stuff on the board. But if you're a visual person and you want to see it, I am on page 622. So if you want to look at that in your book, I'm on page 622. All right. Okay. So on page 622, it says, write expressions for Kc and Kp if applicable for the following reversible reactions. So the first reaction there in our book, it says that you've got HF, so an aqueous solution of HF, plus you've got H2O liquid.
Wait, what number is this?
So this is on page 622. Yeah, it's like example 14.1. Yeah, example 14.1. So this is liquid, and it's going to produce, and it's a reversible reaction, the hydronium ion, which is H3O plus, aqueous, plus a fluoride ion, aqueous. Okay. All right. So they want us to write equilibrium expressions for Kc and Kp. Okay. So let's start with Kc. Because of the fact that we're focusing on homogeneous equilibrium, you only want to write the expression for the things that are in the same state of matter. Okay. So which things are going to be excluded? Which things are not going to be written in our equilibrium expression? The water, the liquid water, right? Okay. So having said that, can you go ahead and write the equilibrium expression? And don't include the water. So can you write like the equilibrium expression, but don't include the water, don't include the liquid water? Think about what would go on top of the expression and what would go on the bottom. Nah, just put it against the wall. I don't even know. Yeah, just, yeah. That's what that means. Not gonna do it today. All right, so what would go on top of this expression? Brackets.
Would it just be
Bye, Maddie.
all the products?
Yep, all the products. So I'm going to do H3O plus, and I'm going to put it right next to that fluoride ion.
Can you not put it in the same box?
Nope, because you want to show, you're going to have two different concentration numbers here in a minute, okay? So you would show that I'm going to have this times this concentration times this concentration, divided by, we're going to put the HF on the bottom. Okay, just like that. So that's the Kc expression. That's the concentration equilibrium expression. And the reason why we write that is it's to give us an idea of like where we would put numbers, because that's how we're going to use this. Here in a minute, you're going to get some actual concentration numbers. And I'm going to ask you eventually to predict if you had a certain concentration for these, would you predict that the reaction would shift to the right, or is it going to shift to the left? And you're going to have to calculate the Kc and figure that out. Okay. Now, the other thing it asks you to do, if possible, is to write the Kp. Can we write a Kp for this? Can you write a pressure constant? You cannot. Why? There's no gases, right? They're all aqueous. In order to write a Kp, you really need to have gases. Okay.
So what if you have one gas?
Oh, then you would just use that one and write its own equilibrium expression. By the way, you could do a KC, it's called like a KC prime if you wanted to.
No, thank you.
I know, right? Yeah, because
Yeah, don't say
no prime? I'm sorry. Does it give you nightmares about calculus? Oh, good. Prime.
And I have to find a derivative.
Oh, we should.
No.
Fun stuff. Oh, yeah.
Derivatives and
Or you just, if you ever say antiderivative, I will walk out of this classroom.
Oh.
Sorry. It will happen.
How about pro-derivative? Like what if I'm not anti-derivative, but pro? Oh, like four derivatives.
I don't know what that is.
Yeah, that's fine.
All right. Okay. So no derivatives, and this thing right here, like right now, I'm not even worried about that. But you were asking, what would we do if there was like a gas or a different state? You write its own equilibrium expression for that. Okay. But the other thing is this right here, they're making an acid solution is what the person is doing. They're just pouring some acid into water and they're creating like an acidic solution. Okay. And, the water would be present in such a large amount, like you wouldn't even have to consider it with this right here. It wouldn't even really matter because the water's going to be, you're going to have so much more of it. We'll talk more about that later, but in other words, this doesn't matter. The main things that matter are the ones that are aqueous. Okay. All right. So having said that, then that problem would be done because we don't have a KP. All right. So let's move on to the next one, okay? The next expression, it says that you have 2NO plus O2. 2NO, that's gas, plus O2 gas. And then yields 2NO2 gas. All right? All right. So can you guys write the equilibrium constant, the concentration constant, and the pressure constant for these, for this one? See if you can. Okay. So what would the KC look like? What do you guys think? Nikki, did you get this one?
Yeah, wouldn't it just be NO2 in a bracket and then the second power over NO bracket, the second power, and then O2?
Yeah. Good? Yeah. And then how about KP? How would we write that?
Do you have to put the coefficient like the same for the KC for the KP?
So yeah, you still do like pressure of whatever the NO2 is. So pressure squared for the NO2 over, you do the pressure squared of the NO, and then the pressure of just the O2. Okay.
What about the coefficients?
And so like the coefficients, you do have to account for them. So like I would square that pressure, whatever pressure value they give me for the NO2, I would need to go ahead and square it and show that you're squaring the pressure.
So that's the 2.
That's, yeah, that little 2 right there, that's where that's coming from. Those little exponents, you'll notice I didn't put one on like the PO2 because there's just one of it, right? There's just a coefficient of 1. So does this make sense? That's how you would write the KC and the KP expressions. Now, all that would be done now at this point is I would give you numbers. I would start chunking them in there and actually figuring out KC or KP, all right? So let's move on and actually try this out. So take a look at, if you're in the book, 623, we're gonna look at example 14.2, okay? Now for this problem, they tell you, now it's the same formula, so we're still looking at this same formula right here, the NO2. But now they give you some information. They tell you in one experiment the concentrations are found to be this. And so the NO, they said, is 0.0542. 0.0542 M molarity, right? Molar solution. And then the O2 is 0.127. And then for the NO2, they tell us it's 15.5. That's a molar solution, okay? All right, it says calculate the Kc of the reaction at this temperature, okay? So if they're telling us to calculate the Kc, we need to know the Kc expression, right? Which is what you guys already wrote down. So you're going to use that same Kc expression, but now we're just going to start plugging in the numbers. So plug in your numbers. If you've got a calculator there, you can go ahead and try this out and see what you end up with. Okay,
Did you get a really big number?
I think so.
Like,
Yeah, like something like 64,000 or something like that. That sound right? Or 640,000.
honestly, I got 644.
Okay. So Kc, Nikki, what'd you get?
I got 644,102.
Okay. And remember, no units, it's just a number. But this number does tell you a lot about this reaction. Is this number greater than 1? Yeah, a little bit. Okay, so it's greater than 1. So would you say this reaction would favor the products or the reactants? Yeah, it's going to shift towards the right. It's going to keep producing product at an extreme amount, right? Because it's a very large Kc. So this reaction would favor product because it's greater than 1. So favors the product side. It's going to shift to the right. Okay? All right. By the way, not to be picky, a little bit picky, you'll notice that how many significant digits do you have here in these? 3. So really, with this number, what would you need to do to it?
Round it to 644.
Yeah, you could do like 644,000 or do scientific notation. Either one. Okay. All right. So there you go. Let's try it again. Sorry, I gotta not on 3:30. Okay. So how about it's Maddie asking about conferences, like CAP conferences. You gotta make your schedule. Which day? I don't care.
Trying to derive problem.
Do what?
Trying to derive problem.
Yeah, probably is. Evil genius. Is IDC, is I don't care, right? Just making sure. All right, let's try again. um, okay, so let's keep going then. All right, let's go ahead and we're going to go onto page 624. So page 624, and we're going to be looking at example 14.3. This one, they are asking you to figure out the KP. All right. So
Are these problems a full page?
no, not a full page.
Well, because you went from 14.1 was on 622, then 14.2 is on 623, and now 14.3.
No, they tell you how to do them, like on these samples. No, really, they show you. See, look, show her.
Okay.
Yeah, see,
Check.
it's all right. Okay, so take a look. We're on page 624, and this is a KP problem. I don't know that we're going to go over this one though, because listen, if you can do these, you can do KP. Because it's the same thing, it's just you're using pressure. You would set them up the same way, products over reactants, and make sure you turn the coefficients into exponents, right? But just so you'll listen, on for example 14.3, it says find the KP, the equilibrium constant, and then it gives you a reaction. They're all gases, so it's all homogeneous equilibrium, and they give you the pressures. It's found to be 1.05 at 250 degrees Celsius. Oh wait, I lied. Oh, this one is different. Okay, let's try this one out. It's just a smidge different. We'll see if we can do it though. Okay, so page 622, 624, dang it. Page 624, we are gonna try this one. I don't think you're gonna have any trouble with it, but it is a little bit different. So page 624, you've got PCl5 in equilibrium. It reacts to form PCl3 plus Cl2. And these are all gases, right? These are all gases. Now let's write down what we know about the problem though. They tell us that the KP for this is found to be 1.05. The KP is found to be 1.05 at 250 degrees Celsius. Okay, so that's something we know about the problem. And it tells us if the partial pressures of PCl5 and PCl3 are 0.875 and 0.463 respectively, so I'm going to go ahead and write that down. So we got 0.875 atmospheres and 0.463 atmospheres. They want to know what's the partial pressure of Cl2. So they want to know what's the partial pressure of Cl2. Know what to do? Right. So let's just set up the problem. Yeah, Sky said yes. So like yeah. So go ahead and let's set up the problem. Okay. You're going to solve to find your missing pressure, your missing partial pressure of Cl2.
Oh, we all just sat here and you're like, great.
No.
Okay.
I'm telling you, I look at Sky, she makes me giggle, and I look at her to see if she's going to agree with something. She does. I say the word balls, she laughs. See? Told you. Okay, so set that up, see what you can get. Okay, what do you think? Anybody get it yet?
I got 1.984.
So 1.984, I'm gonna go ahead and just do 1.98. And what would the unit be here?
ATM.
ATM, good. Because it's the partial pressure of chlorine gas, so 1.98 ATMs, good. All right, make sense? Good. All right. Moving on. Last example for the day, and then you'll get your practice problems. And remember, we're still dealing with just homogeneous equilibrium, okay? So methanol is manufactured by this reaction. So you're making methanol, and the reaction looks like this.
What problem is it?
This is sample problem 14.4 at the bottom of page 624. Okay. And I've got carbon monoxide gas, so CO gas, plus hydrogen gas. And that's 2. Sorry, I forgot my coefficient. 2H2, CH3OH. CH3OH. And I guess it goes without being said, I just forgot to say it. You gotta always make sure that before you write these things that they're balanced. So in the book, hopefully they'll tell you like if it's not balanced, but just make sure and check them. Okay, so it's asking us though, it says the equilibrium constant, so the Kc, I'm just gonna write down some things that I know. The Kc for this reaction is 10.5 at 220 degrees Celsius. So my Kc is 10.5 at 220 degrees Celsius. Okay, and it says, what's the value of Kp at this temperature? Okay, so what's the value of Kp at this temperature? Okay, all right, so let's go ahead and try this out. Now here's the problem. You can't get Kp just based on pressures because we don't have them, right? We don't have any partial pressures of the system. But don't we have another equation that would help us get the Kp based on Kc? And we do, right? So we said earlier that Kp is equal to Kc times RT raised to the delta N power, the change in your moles or coefficients, okay? So plug it in, see what you can come up with. Oh, and before we do anything else, what do you need to do with this temperature? Yeah, it's got to be Kelvin because that R is in Kelvin. So that's going to be 493.
So for the change in coefficient, would it be 0? Because there's 2 minus 1 minus 3.
So 1 minus 3. No, I think, let's see.
The coefficient? Yeah, coefficient is the one, the 2 in front of H2, that's a coefficient. Yeah, so
It'd be 1 minus 3. Yeah. And so you end up with a -2. So you're going to raise it to the
Okay, so you
negative
have to,
second power. Misconnection. Sneak it in.
Are you relating to pay dues too?
Yes, so junior dues?
Yes.
Okay, yeah. I will get you a receipt written and get it back to you.
I'm not free.
Okay,
Oh, you know where I'm at.
I'll find you. All right, thanks. All right. So, but yeah, we're just gonna raise it to the negative second.
did you get 0.006409?
493. Okay. So what'd you get, Jimmy?
Me and Nikki got 0.0061.
Okay. So KP 0.0641.
0.
There we go. Like that?
Yeah.
Okay. So if I ask you, which way would you predict the system to shift?
To reacting.
To the reactant side, it would shift towards the left because KP is less than 1 here. Let's see here. Yes. It's everything. The only other thing that they tell you here in that practice exercise is, oh wait, and I lied about that. I think KC, like it would still shift to the right. I don't know that you can do shifts based on KP. I think you have to determine shift based on KC. So KC at this temperature is still 10.5. I think it would still shift to the right. I don't think you can base it off of KP. I'll double check that, but okay. All right. Anyways, the only other problems that you're going to have though with the practice would be where you're just manipulating this formula to find different things. That should be what the practice problems are. Okay. So your practice problems that will be assigned to you, it's going to be, and I'll post this later to Kieran. I'll put it up on the site, but it's on page, I have to write that down. It starts on page 649, and you're going to do number 14.7, number 8, and then finally 16, 17, 18, and 19. So you'll do number 7, number 8, and then 16 through 19. And that starts on page 649.
And when does this due?
Let's go for Thursday. I'll give you 48 hours. All right. Does anybody have any questions? That's your Win Wednesday assignment though. Okay. So that'll be it, but I'll post that later too. So, okay. Any questions? Nope. Okay. Yeah, I know. I can hear you. But I read your lips, so.
Okay.
Bye.
Bye.